Hi class, this is obviously Mr. Perry. I hope you guys are well. Before we get into Chapter 2, we need to review another pretty important fundamental algebra concept, and that's simplifying and working with radicals. You see the radical sign in the 6th and 7th grade when you first learn how to work with square roots. And the first square roots you work with are perfect squares. So, you'll remember the square root of 4 and the square root of 16 and the square root of 49, whatever. Those are all perfect squares because they can be simplified to a whole number. The square root of 4 is 2, 16 is 4, the square root of 49 is 7. So in the past, unless you've had a perfect square, there's really nothing you can do. So for instance, if you've got the square root of 5 or the square root of 6, you would just leave it alone and write it square root of 5 or square root of 6. You could always approximate it. For instance, the square root of 6 is in between the square root of 4 and the square root of 9. So I might guess that it's 2.4 or something like that, but I wouldn't simplify the square root of 6. Now, what happens when you get an imperfect square that has factors in it that are perfect? So for instance, one of the most famous is the square root of 8. We know 8's not a perfect square because we know there's not a whole number that when we multiply it by itself gives us 8. But I can rewrite the square root of 8 as the square root of 4 times the square root of 2. And that's a property of exponents, really, that we learn in 8th grade that says the square root of any number, AB, can be rewritten as the square root of A times the square root of B. So since we know that A can be broken up into two factors, we can write it as a product of those two factors. So if we rewrite the square root of 8 as the square root of 4 times the square root of 2, we then see that square root of 4 is a perfect square, and we can rewrite it as 2 square roots of 2. So while the square root of 8 is a radical, we would call that unsimplified, whereas the 2 square root of 2 is indeed simplified. Let's do a couple more. Let's try the square root of 20. I know a handful of numbers that can get me the square root of 20. And the first one that comes to mind is 4 and 5. Square root of 4 is a perfect square, so I'm going to take the square root of that and get to 2. I bring down my square root of 5, and I've rewritten the square root of 20 as 2 square roots of 5. Now this should remind you a little bit of working with factor trees, and it's very similar. In fact, there's different means to the same end. So if you happened not to, if square root of 4 and square root of 5 weren't the first two squares that came to your mind as factors of 20, maybe instead it was 10 times 2. Well, 2 is not a perfect square, nor is 10. However, we can drill down on the 10 a bit and rewrite the 10 as 5 times 2. And by rewriting the 10 as square root of 5 times square root of 2, and then bringing down our other square root of 2, we can see that square root of 2 times square root of 2 is the square root of 4, which is 2. Another thing to remember, the square root of x times the square root of x is always x. So those simplify to x, to 2, and I get 2, thanks to the 2 square roots of 2, times the square root of 5. So regardless of which method I use, if I keep going and use a couple fundamental concepts, I'll always get to the same thing. I always like to try and factor using one perfect square, but if in this case you just happen to see the 10 and the 2 and you keep going, you'll always get to the same spot, or at least you always can get to the same spot. Let's try one more with 50. So we got to ask ourselves, what numbers multiply to get 50? We know 1 times 50, 2 times 25, and 5 times 10. Well, since 25 is a perfect square, that's the pair I want to use. So I'm going to rewrite the square root of 50 as square root of 25 times the square root of 2, which is, of course, 5 square roots of 2. Once you get good at simplifying radicals, you'll also find this helps you add numbers that you might not think you can add. For instance, I cannot add the square root of 8 plus the square root of 9. They're unlike terms, just like I can't add the square root of 2 plus the square root of 3. Those two expressions are simplified. There's nothing else I can do. However, suppose I had the square root of 8 plus the square root of 2. Well, the square root of 2 is simplified, so I can't touch it, but the square root of 8 is not. I can rewrite the square root of 8, as we discussed earlier, as the square root of 4 times the square root of 2, or 2 square roots of 2. In fact, I'd really like for you to get in the habit of, as soon as you see a square root of 8, rewriting it as 2 root 2. If I bring down the other root 2, you'll see that what looked like a problem without like terms is indeed a problem with like terms that I can then add. So on the left side, I've got 2 square roots of 2. On the right side, I have 1 square root of 2. So just like 2x plus x is 3x, 2 root 2 plus 1 root 2 is 3 root 2. Let's try one more. Imagine I've got the square root of 50 plus the square root of 32. Well, both of those have a perfect square in them. 50 is 25 and 2. 32 is 16 and 2. The square root of 25 is 5, so I bring down my root 2. The square root of 16, of course, is 4. All of a sudden, I've got 2 like terms. 5 root 2 plus 4 root 2 combines to get 9 root 2. And notice the terminology I'm using. 9 root 2 means I have 9 square roots of 2, or 9 times the square root of 2. And that's how you simplify and add radicals.